Hi, here we are discuss about a project, the extractions of fetal ECG from abdominal and thorax ECG using a non-causal adaptive filter architecture. So here the proposed architecture, the extractions the fetal ECG from the maternal abdominal ECG signal is a challenging task due to the various artifacts. This study proposed an enhancement to the non-causal adaptive filter architectures by incorporating two different multiplier designs. One is a array multiplier, another one is a Vedic Bahum multiplier to analyze the area and power efficiency. Additionally, the applications of the non-causal adaptive filter is extended to the invasive FECG method for validation. Furthermore, the non-causal adaptive filter is adapted to extract the maternal ECG from the abdominal signal, utilizing direct fetal ECG as a reference. The dual extractions capability aims to facilitate the further heart rate analysis for both maternal and fetal health monitoring. The architecture was implemented on the Virtex-7 FPGA, achieving optimal performance with reduced power consumptions and enhanced resource utilization. So this work provides a robust solutions for comprehensive maternal fetal ECG monitoring, offering the potential improvements in the clinical diagnostics and the maternal fetal health management. Now we can verify the paper. So this paper is fully designed for the extractions of the fetal ECG from the abdominal and thorax ECG. So here the thorax ECG means it will be taken from the heart of the patient, and abdominal ECG it's taken from the abdominal from the patient. Okay, so here once we are taken the abdominal ECG, it will be mixed with the thorax. Okay, we need to filter and we need to extract the FECG method only. So that is the concept of this paper, but we have modified this architectures. Okay, so here we have two different applications. One is a invasive method, another one is a non-invasive method. So here first of all we need to understand what is the invasive and what is the non-invasive. So this is a reference architectures for invasive versus non-invasive method. So the figure 5, okay, so the A equal to non-invasive FECG measurement and B equal to invasive FECG measurement, and this is one more reference for the invasive measurement. Okay, so how they are taken the ECG signal from the invasive and how they are taken a ECG signal from the non-invasive. Okay, so this method, the invasive part we will get more accurate, but a non-invasive part it's a safety purpose, but it will be not get a more accurate signal. It will be get a approximate signal only. For accuracy we will move for this proposed architecture of the invasive method. So we have modified this architectures to invasive method with a abdominal and direct ECG based architecture. Okay, so this architecture, filter architectures, it will be same for this application, non-invasive or invasive method. Okay, now we can analyze the filter architecture. So this architectures give up with here the figure 2, the block diagram representations of the proposed non-causal adaptive filter. So here initially we are given a thorax ECG signal. Okay, so which one we need to give a input, that is a mixed signal. Okay, so it's a thorax ECG means it's a direct signal. Okay, so this is a abdominal signal. So abdominal signal is given with here they are subtracting the signals with the support of the error computation block. Okay, so here this n single tap FR filters they are used, okay, to filter the signal. After that they are separating the signal. Okay, and after that they are calculating the error, that error to give up with the coefficient to the n single tap FR filter. Okay, but here the FR filters means it will be taken the coefficients from the MATLAB, but this is an adaptive filter. So adaptive filters, it will generate the coefficients automatically with support of the feedback input. So we are calculating the error, that feedback we are given again to the coefficient of the n single tap FR filter. So that support it will be given with adaptive weight update model and step size update model. Okay, and some estimations will are calculated for the FECG method and also for y of n, their error value. Okay, so the brief architectures it will be given in figure 3. Okay, so this is a brief architectures, and step size calculations it will be given in figure 4. Okay, so as per this architectures we have developed the Verla HDL code, and this architectures it will be differentiate with two different comparisons. One is for array multiplier, another one is for Behum Vedic multiplier. Okay, so array multipliers means it's a normal traditional multiplier, so it will be take more logic sizes. Okay, and Vedic Behum multiplier means it's a reason multiplier, come up with less logic sizes. Okay, so we are compared both of things. Okay, that will be implemented in the coefficients. So this coefficient multiplication, but here this coefficient multiplications, it's a 3 operand multiplications. Okay, so it will be multiplied with mu and x of input and error input. Okay, so this 3 operand multiplier will taken as a output. Okay, so this 3 operand multipliers means it's a cascading method based multiplier. Okay, and this is a reference paper for 8-bit Vedic multiplier using Behum adder. Okay, so this is the architecture we have used the paper. Okay, so 8-bit, and this is the array multiplier. It's a traditional multiplier architectures. Okay, so this is the architecture of the array multiplier. Okay, so here, so this is a reference signal for maternal and fetal ECG. Okay, so this architectures we have implemented here. This is a test bench of the coding. Okay, so the two signals we have generated, one is for abdominal, another one is for direct signal. Okay, so it will be taken from the database. Okay, and it's given as a file reading code. Then we are read the signal and it will be given input to the top model architecture. So this is a direct FECG method and this is a abdominal ECG method. Okay, so this signal we are given into the N single tap FR filter and adaptive step size model and error computation block. Okay, and some estimation for YN and some estimation for EN. Okay, so the internal architecture it will be given in the separate code. Okay, and this is for Vedic multiplier architectures code. Okay, so this two simulation method we have done within modelism. Okay, so this is a simulation output for a normal array multiplier, and you can analyze the abdominal signal, direct signal and external extracted maternal signal. Okay, so before that you need to analyze the paper output. Okay, what they are given in the non-invasive method. Okay, why? Because we are shown only the invasive method in the modelism output. Okay, so this is a non-invasive method based architectures. Okay, so here this is the abdominal signal. It will be mixed with the maternal and FECG method. Okay, so here this type of signals. Okay, maternal and FECG method. So this signals we need to subtract the thorax signal. Okay, so thorax signal means maternal signals we need to subtract it. Okay, then after we'll get a FECG signal as a output. Okay, but in the modelism output it will be different. This is the invasive method. Okay, so here the abdominal signal mixed with the maternal signal and FECG method. Okay, FECG signal. Okay, so here small peaks available, right? So this small peaks is a FECG input. Okay, so it depends upon the data sets, it will be came maximum or minimum. Okay, so and this is a direct FECG method. Okay, so why we are go for this applications means it will be come with more accurate the direct FECG method to identified some more applications, example heart rate calculations or arrhythmia calculations. So that kind of calculations we can use this direct FECG method and this extracted maternal ECG. Okay, so here this extracted maternal ECG we have subtracted the FECG method. Okay, you can analyze the FECG signals not present in the output, final output. Okay, so we can calculate heart rate for both direct and external ECG. Okay, so that is a future applications we have subtracted in the invasive method. Okay, so here this is a simulation output for Vedic multiplier, and these two architectures we have synthesized in Xilinx VADO Virtex-7 FPGA. Okay, so here the comparisons analysis I can analyze it here. It will become with LUT 4786, LUT RAM 74, flip-flops 446, IOB and BUFG, and this is a power report, and you can analyze the RTL schematic here. Okay, so this is the RTL schematic for the architecture, so error computations, adaptive step size, and n single tap FR filters and some estimations. Okay, and this is for the Vedic multiplier comparisons. Okay, it will be take very less logic sizes. Okay, 2847 and 10 in the LUT RAM, 243 in the flip flops IO based PUBG. Okay, and power consumptions. Okay, so this comparisons we have plotted in the table. So this is a paper comparisons here. Existing utilizations means paper comparisons. Okay, so they are given here. Okay, n equal to 8. So this part only we have developed it here. Okay, and this comparisons updated in the graph also. Okay, and we have written an abstract document for this project. Okay, so title, base paper abstract, improvement of the project, proposed title and proposed abstract, existing system, disadvantages, proposed systems, and invasive FECG method, non-invasive FECG method, advantages, and Vedic multiplier nodes and related nodes for this project. Okay, and finally come up with literature survey here, literature survey and references. Okay, thank you.